Good morning, everybody. For those who just joined, can you just tell me if you today I wanted to share the whole window with you. So just to make sure now, can you see my actions in the whole windows? I'm not sure what's going on because it seems like. Okay. Shall I share the desktop? Maybe sharing the desktop option is the right option. So now, well, can you say a page with course material, chapter 1, 2, 3, and so on? Is this what you see? Yeah? Okay, this is the case. So what I will do today, I'm going to start chapter 6. Just 1 second. Okay, now with this chapter, actually what I need from this chapter consists of several sections, but it's all going to be covered in Think 212. What we need for today is only covering 2 sections only, which are 6.5 and 6.6. And I will emphasize on the most important things that are needed in this chapter, because the idea behind giving this chapter is just to have an introduction to chapter 7. So that's basically the idea. So from the title, it is titled as Thermodynamic Properties of Fluid. And what I want to do here in this chapter, I want to cover 2 sections, while one of the sections is related to how to get the properties from the diagram, and the other one is how to get the properties from tables. And I will emphasize more on section 6.6 because we will need it a lot in chapter 7. That's basically the overall idea. Now, when we start with the diagrams, I already did in chapter 3, if you remember, like full detailed explanation on how to read PV diagram, TP diagram, and TP diagrams. Those are the most important diagrams that we covered there in chapter 3. Just to complete the picture, actually the properties of any fluid can be like temperature, pressure, volume, enthalpy, and entropy. And entropy has been recently added from chapter 5. Now, the most common diagrams here that I want to show are those. Here we have pH diagram, and actually pH diagram is normally presented as len P versus H. We have another diagram that is called TS diagram. We have other diagram also that is molar diagram. Those 3 diagrams are really important diagrams, all right? Are we going to use those diagrams here in the course? Maybe, or in Chink 211, maybe not that much, but maybe good to illustrate on some more important characteristics in the diagrams. If you remember with the TP diagram that I explained before, I'm just going to show you just a comparison here. With the TP diagram, which was the phase diagram, if you remember, it was something like this. The pattern looked like that. And when we talked about the phase, solid, liquid, and vapor, we mentioned that the changing in phase or the saturated mixture phase was represented by lines. Like, for example, here, the line between liquid and vapor, this is the line that represents the saturated mixture. Now, in comparison, those diagrams that I'm showing to you here, representing those mixture phases as an area. For example, here is the area of the mixture, liquid and vapor. Same thing here with the TS diagram. Now, this is because the diagram is just 2D diagrams, and that's why when I change the diagram from one to another, you may change the phases from line to an area. That is one thing. Another thing, and same thing, you notice that with the TV diagram and PV diagram, where the mixture region or the 2-phase region represented by an area. Same thing with the critical point. Make sure that you know the critical location here, where the left side of the critical shows the saturated liquid region, while the right side here represents the saturated vapor region. And I already mentioned that before. I'm just highlighting the most important things with the diagrams, just to make sure that you get an idea on why those diagrams are useful. Generally speaking, whenever you have a property, the interaction, for example, here, once you have the pressure and enthalpy, you can just define the phase and be able to get other properties accordingly. Another thing that is really useful when you go and have a look to the diagrams, you can also see different regions, and you have, as we mentioned before, you have the subliquid, you have the saturated liquid, you have the saturated mixture, and then you have the saturated vapor. Remember that this region represents the superheated, and when I say superheated region, it simply means that from the term, it is superheated, so I am superheating it. It means the temperature here is higher than the actual temperature, which is the saturated temperature at that pressure. So when the temperature exceeding the saturated temperature, then this will be the superheated. So that's with regard to the pH diagram and the TS diagram. Even with the molar diagram, it is useful. It represents the relationship between H and S. Something interesting about this diagram that it doesn't show the volume effect. And look here at constant pressure, you have a line or a curve. For constant temperature, you have a curve. But for the volume, maybe there's no such a curve for it. In higher level courses, you are going to use this diagram quite frequently, but I just want you to get an idea of what's happening here, right? And keep in mind that regardless of the diagram, you can always shift from one phase to another. I'm just going to show you an example here. An example here, like this line, 1, 2, 3, 4. You can see at the same constant pressure, you can shift from liquid phase to saturated liquid, and from saturated liquid to saturated vapor at the same pressure. You are keeping the same pressure. And if you remember, I gave a full story of what's happening when you boil. If you have a boiler at constant pressure, you can shift from one phase to another. And I explained that when I give you the PV diagram and the TV diagram previously. So that is one thing. Another thing is the diagrams that includes entropy in the x-axis are very useful diagrams, because whenever you have asentropic process, then it means you do have vertical line. And vertical line means you are moving where delta S is equal to 0. Means moving from state 1 to state 2, it can be useful to read other properties, whether it's in HS diagram or in the TS diagram. Those are just general explanation of how those diagrams are important. And as I said, here in Ching 211, I'm just going to explain the general ideas behind those. We did use a PV diagram, TV diagram, and TV diagram previously. We will be using HS diagram also in chapter 7, but the rest, I think he will cover them in more details in other chapters. That's 6.5. By the way, chapter 6 can be finished in one lecture, but I want to emphasize on something very important today. How can we read the table of thermodynamic properties? What I did, actually there is here you can see Smith putting several explanations. I would use my own way to explain how to read the properties, and that's why I ask you to bring your table with you. So what I will do today, I will show you, we'll go to the to some examples. I want you to keep the book in front of you. I'll talk about the tables in detail. So what we are going to do, you can see those here. We have several information. I will explain all that today, but I will not explain example 6.7, simply because I want to make sure that you can read the tables of properties, and then we will do application next lecture. So that is the plan for today. So go back from here. Please let me know if you cannot see the appendix. I'll try just to put the appendix here with you, where I can find it. To get it. Okay, I wasn't planning to get this version, but anyhow, since I opened that, I do have another better resolution, but since this is the one. Okay, can you all see the textbook? Just to make sure, can you all see the textbook, guys? Yeah, it's page 716, but I need to open it with you so that all can see it. Oh, okay, there should be a much better way to open it, but it seems like, okay, let me just try something else. Okay. It seems this PC doesn't allow me to open it using PDF, so I have to open it online. That's okay. So maybe this is a better way. Okay, so what we have for today, we have thermodynamic properties. Where are they? They are in the tables, and the tables we are talking about in the 6th version and 7th version, they are Appendix F. So you can see here a steam table. Okay, all right. If you cannot see, just to double check. Can you all see the table, guys? Can you see the tables, guys? Yes? All right. So what do we have today? I want to make sure that you can read the properties in the table. So what do we have? We have 4 different tables. Table F1, and it is titled as, you can see here, it's titled as saturated liquid. And then we have table F2, and table F2 is titled as saturated steam again. So both of them are saturated. So table F1, that's table F1. Table F2, it is superheated. You can see there, it is superheated. And then I have I have table F3 and table F4. Now, what's the difference? First of all, I have to clarify what's the difference. Table F1 and F2 are 2 tables that shows saturated liquid for F1 and superheated steam for F2. That's number 1. Then we do have table F3 and F4, and the table F3 and F4, when you go and have a look, they just come after F1 and F2. Those 2 tables are the same, but in English system. So that's the only difference. This is number 1. Easy. Number 2, how can I read? When you go and have a look, for example, we'll start with, here, I do have page, maybe different versions than yours. Table of 1, I'm opening page 666. But I think based on the version you have, table F1 starts 716. Okay, when you go and have a look to the table, you will find that the table consists of the following. Now, it is saturated steam, and when I say saturated steam, means it is in the saturation condition. And I hope you all know where the saturation condition on the PV diagram, based on chapter 3, I explained that clearly. Now, the information given, you have T, you have P. Now, keep in mind, if you apply the Gibbs phase rule for a pure substance, and it is saturated liquid, then you need to know 2 properties to fully define the system. Now, from now you have to know that temperature and pressure with saturated condition, they are dependent. Dependent means what? Once I give you the temperature, the pressure can be found. So actually what you need to know to find the properties of saturated steam, it is one of those properties plus another property. What is the other property? It is this. When they say it is saturated steam, now they have to define exactly what is it. I want to clarify this on charts. Saturated steam means, I'm just going to draw a PV diagram. Just as an example, you can draw a TV diagram if you like, but I want to emphasize on what saturated means. When I say saturated steam, it can be at point number 1, which is saturated liquid. It can be at point number 2, which is saturated vapor, or it can be in between, which is saturated mixture. Okay, so the saturated here means 3 things: either saturated liquid, or saturated vapor or saturated mixture. Okay, and this is very important. الحين, how to read the properties? If, for example, I told you it is saturated liquid, then the way you have to get the information here, for example, if I told you that the temperature is 20 degrees C. 20 degrees C, this is the temperature in degrees C here, right? So 20 degrees C means you have to go at 20 degrees C horizontally, and then read the properties. And the properties you can see from the table, you have the specific volume, and the unit is written there, specific volume, it is in centimeter cube per gram. You have internal energy, and the unit here it's written in kilojoule per kilogram. You have enthalpy, again in kilojoule per kilogram, and you have the entropy in kilojoule per kilogram Kelvin. Okay, so how can we read the information? If it is saturated liquid, all you have to do is to go and get the liquid properties. Okay, you can see for each property here, they put saturated liquid, they put saturated vapor information, right? Same thing here, saturated liquid, saturated vapor information. And then saturated liquid for the enthalpy, saturated vapor for the enthalpy, and so on. Yani, if I told you that it is saturated liquid, then all you have to do is just to focus on what? On the liquid properties. Where are those liquid properties? You can just get them here. Look, this is liquid, right? So that's about the saturated liquid. Then the question here is, what if it is vapor? Same thing, because you can clearly see from the table, at the same pressure, at the same temperature, this is the line, I am getting 3 points here. At the same Tsat and Psat, those are called Tsat and Psat because they are the saturated temperatures and pressures. I may have liquid, if it is saturated liquid, I can get the properties of liquid. If it is saturated vapor, I can put the saturated vapor and so on. Now, here is the point. So with liquid, we have no problem. With the vapor, we have no problem as long as they are saturated conditions. The problem would be what? If it is saturated mixture. Saturated mixture means what? Means it is any point on this region. You can see I'm not showing one point. I'm showing a region between liquid and vapor. And what will define that mixture? Please bear with me. It is very important. Whenever you have saturated mixture, means I'm having liquid and vapor in the same container. And how much I have of that liquid, how much I have of that vapor, it really depends on the fractions, on the composition. For that reason, today I want to define the mass fraction as what is called quality. Quality, this is called quality. X is called quality in thermo. And the quality is defined as mass fraction of vapor, yani mass of vapor over total mass of the mixture. Why, Doctora, is this? Because based on the mass fraction, I will be able to decide where is my point. I'll give you an example. If my X is equal to 1 means what? X is equal to 1. If X is equal to 1 means it is totally vapor. Totally vapor means it is saturated liquid. X related to the quality of vapor. So X means it is totally vapor. Here X is equal to 1. Okay. However, if my X is equal to 0, 0 means what? Means no vapor is there. In other words, I do have here as X is equal to 0. The quality is related to how much vapor I'm having. So if I don't have any vapor, means it's saturated liquid. If I have all of it vapor, then it is saturated vapor. What does this mean? This simply means that the region between liquid and vapor, it means the quality it's between 0 and 1. The more is X, the more I will be towards vapor phase. In other words, if X is equal to 0.8, you'll be probably here. X is equal to 0.5, then I am in the middle. X is equal to 0.2, then I am closer to the liquid phase, and so on. And then, Doctora, how can I convert? How can I find the property? And then, let me see. And that is very important. So what I will do, I will go through each table and explain that in detail. Look here, guys. Whenever you have a table and you want to know the properties of liquid, we say we have no problem. Liquid, property of vapor, we have no problem. But we do have something called the quality, or we need to find the quality or the properties of, the properties of mixture. So that table doesn't show the properties of the mixture. It shows something in the middle, and that in the middle called evap. Evap is simply the property of vapor minus the property of liquid. And I will tell you later on how can I use it to find the properties of mixture. That is only the difference between the column that comes after it and the column that comes before it. Now what I did here, I did MV minus ML. M means any property. M means property like specific volume or enthalpy or internal energy or entropy. That's what M means. So for that reason, what I did here, I just called it M so that you know that M is related to any property. So that's number one. Remember, table F1 and F3. Table F1, it is SI system. Table F3, it is same for saturated steam, but for English. So table F1 will show you how to get the properties for liquid phase, for vapor phase, for mixture, but that is if it is saturated. خلاص؟ With the superheated, the case is quite different. Remember, I did not mention how precisely you can calculate the properties of mixture. I will explain it later. Now I just want to make sure that you can read the tables. When you go to table F2, it is superheated steam. And with the superheated steam, again, the two properties you need to know is any two properties. Now you can, by the way, with the first table, I may not only give you the temperature and saturated steam, I can give you the saturated property and the temperature, or the pressure and saturated property. In other words, any combination between two properties, you have to figure it out here. Where is it? For example, at a temperature of 20, I may not give you, for example, a temperature of 20, and I said it is saturated mixture. But I said that, okay, we'll go to that later on. But I may give you a temperature, and I give you another property here that you have to figure it out. Okay? يعني, not necessarily to be only the temperature. Okay? Another example. I can tell you, for example, it is saturated steam, it is saturated vapor. That's one information. The other information is that the enthalpy is 2487.4. So you will just go and find where is that in the table. And this will identify, maybe I'm wrong here. 2400 for saturated vapor. You will go to saturated vapor and try to find the value. So here, if for example, I told you it is 2529. So you will just go and find it out. And then because of that, you will be able to define what is the temperature for me, what is the pressure, which are the saturated pressure, and all other properties can be defined as well. خلاص? This is how it is. Same thing with table F2. Table F2, it is the same. You can again giving two properties. I will give you example. I may tell you, for example, that now with the table F2, let me just make sure that you can read it. With table F2, it shows the first column shows the saturated properties. يعني the pressure here, it shows the pressure at the top and the temperature in degrees C below it. So at a pressure of 1 kilopascal and the temperature of 280.13, those are the saturated properties, okay? Or the saturated condition. يعني this is PSAT and this is TSAT. Instead, Dr. superheated means not TSAT, it is a temperature above TSAT. Yes, that's why what we did here to make the picture complete for you, we put the pressure, we told you that TSAT is that much. In other words, if the temperature is above 280, then it's going to be superheated, 280 degrees C. So the first two columns actually are not related to superheated, but related to saturated. And then, Victoria, we have table F1 that shows the saturated. Yes, you do have table F1. But here it is like more comprehensive that shows the saturated properties in the first two columns, and then the superheated in the remaining. You can either use table F1 to get the saturated properties or table F2. And then, Doctora, which one we have to use? Which one is easier? Okay, listen to that hint. If the pressure was given in the question, I would recommend table F2. Why is this? Because the pressure here are given as 1, 10, 20, 30, 40, no decimals. So maybe you may find the saturated condition for the pressure given in the question if the pressure is just one value without decimals. When you go to table F1, and the pressure was given, then it's quite difficult to go and read from here because the pressures are given in decimals. You can see there. So I would make a conclusion here. Table F1 is temperature-based table. That is temperature-based. Temperature-based means If the temperature was given, then maybe easier to use table F1 to get the saturated properties because the temperatures are without decimals. If it is a pressure-based, if the pressure was given, then you better use table F2, and that's why table F2, I will call it a pressure-based table. Okay. My advice always before you decide on which table you have to use, look at the value that's given. If it is like, for example, 10, 20, 30, I mean number without decimals, then maybe better to go and use table F2. Otherwise, use table F1. In both cases, sometimes you may need to do interpolation, whether it is single interpolation or double interpolation. Why is this? Because sometimes in the question, they don't give you the exact value of pressure that is available in the table, or they don't give you the exact temperature that is available in the table. So that's why make sure that before you do interpolation, check table F, one of them, table F1, for example, and if you didn't get the data, go back to table F2 to find out if the information is there. If it's not there in any of them, then interpolation is a must. I'm just saying this, just trying to avoid the interpolation if you cannot make it. Okay, so that summarizes how to read the tables. With table F2, as I said, the first two columns are related to saturated properties, whether it's liquid or vapor. But if it is superheated, then definitely, for example, if the pressure is 40 kilopascal, then the temperature will be above the saturated condition. For example, I may give you that the temperature is, let's say, 250 degrees C. 250 degrees C, where can I find it? It's not in the first two columns, but it's after that. So at 40 kilopascal, I have to go horizontally and see where is 250 degrees C. Keep in mind that the temperature here are written in Kelvin for you, as well as in degrees C. And once you get that, you will find all properties written. And you can see there, the properties are those, which are V, and then U, then H, then S. You can get them one after the other with the same unit that we defined in table F1. This is how you read the information. Okay, so basically this is the idea. Now, what I want to do now, before we solve any example, I want to do a supporting, well, I called it supporting material. But why I did this? Because I want to make sure that when we start solving the problems, you can define the phase. So let's see what I prepared for you today. I hope that I will be able to get it, because that I think I prepared some material here. Yeah, okay. So what I want to do, I prepared a table. I want to make sure that you can all read the table F1 to F4. So I did a class activity here. Please keep the book with you, because I don't want to open both at the same time. Keep the book with you, in front of you. And here I want to clarify what we are going to do if we have been given a property that is not complete, and you need to complete the properties for any given information. So first thing here, we do have, I just put several information for several cases. And tell me here whether the phase is, describe for me the phase. Is it saturated liquid? Is it saturated vapor? Is it compressed? Okay, what I did so far, let me just make an introduction to what we did here. What I did so far, I explained what do you mean by saturated. Okay, so accepting. Let's pick a problem with this desktop. I just want to open it not online, so that. Okay, so I hope it will work now. Okay, let's see what we have. I want to clarify how can I define the phases at several conditions. So let me just give like kind of summary. The phases we have generally we have saturated. Oh, I don't know what's going on here. Oh no. Oh, okay. All right. Okay, I can see, I can do another thing. Let's go here. All right. Okay, let me clarify something very important here. The phases generally we have saturated liquid, we have saturated vapor, we have saturated mixture, and we have superheated. Okay, those are the phases we explained so far. I need to clarify that there is also another phase which we explained in chapter 3, which is subcooled. If you remember, we have subcooled, and we also called that compressed liquid. It is either subcooled or compressed liquid. Okay. What I want to do here, I want to clarify how can I define those phases on the using the table. Generally speaking, let me make a table, maybe easier to clarify the idea. If I have, of course, based on the PV diagram, we have subcooled that comes first, then we have saturated liquid, then we have saturated mixture, then we have saturated vapor, and last thing we have the superheated. Okay, easy. Just for your information, I'm gonna put properties here and make sure that you are aware of that. I will start with the saturated conditions. We already explained with the saturated condition that temperature is actually Tsat, pressure is Psat, and that rule is applicable for all of those, whether it is saturated liquid or saturated vapor. So that is going to be same here, that temperature and pressure are the saturated properties. But when it comes to the property M, then property M means, I will define M here, M can be any property that are H, U, S, or V based on the table. That property M, if you want to get it for saturated liquid, then you will get the liquid properties from the table. So it's ML. While with the saturated vapor, okay, with the saturated vapor, my M here is MV. Saturated vapor, M here is MV. Now, with the saturated mixture, my M is somehow in between M liquid and M vapor. And later on, I will tell you how to define this M precisely. But you have to know now that it is in between M liquid and M vapor. That's with regard to the property itself. Now, with the superheated, we said that it is superheated. So that's why my temperature is greater than Tsat. This is how it is. While it's either temperature that is greater than Psat, or the pressure is lower than Psat. And Doctora, what does it mean? It means that, and for example, I'll just give you an example. If you have vapor, okay, it is saturated vapor in front of you in a container. To make it superheated, you will either heating it up to increase the temperature to be above saturated temperature, or you will reduce the pressure, because if you reduce the pressure, the molecules will be more further away from each other. So that's why it will be superheated. And then, if you know that this is the condition for superheated, then with the subcooled, it's just the opposite. Opposite means what? Means, for example, if you have saturated liquid and you want to make it more cooled, more subcooled, means you will lower the temperature to be lower than Tsat, or you will compress it more to have the pressure with more than Psat. So this is how it is. The idea here is that the way you will find the property, or the way you will define the phase, is by looking at temperature and pressure or looking at the properties. Is the properties is equal to liquid properties? Is the property liquid is equal to vapor properties? Is the temperature and pressure are above or below SAT? Then here you have to decide. And here with regard to the properties, always with the superheated, the properties you have is always greater than the properties of vapor. Always, because you are increasing the temperature or decreasing the pressure, and that's why the enthalpy becomes more than the vapor, the internal energy becomes more than the saturated vapor, the entropy will become more, and so on. So this is how you, and even the specific volume, keep in mind you are heating it up, so the volume will increase. So this is how you define the M, or the M is always greater than the saturated vapor property. طبعا with regard to the subcooled, it is the opposite. M is less than M of liquid. Sorry, why M of liquid? Because you are subcooling it. Okay, I'll just remind you the PV diagram here. You do have here the liquid property, you do have here, this is the PV diagram, you do have the vapor properties. Anything below that region is actually subcooled, and that's why the properties is less than the liquid properties. With the superheated, it is this region and the properties are greater than the vapor properties. So that's generally how to figure out what's happening in each phase. Last thing I want to say is that you may notice in table F1 that saturated mixture, let me just change the color to give another, okay, with saturated liquid properties, you can use table F1, and that is a temperature-based table, and if the temperature was given, or you can also use table F2, because with table F2, if the pressure given, so it's pressure-based table, but if you use table F2, it is only what? It's only going to be the first 3 columns. Let me just double check that they are 3 columns at the beginning, or 4 columns. 1, 2, 3. The first 3 columns. Why? Because the first column will show the pressure, temperature. The second column will show the saturated liquid. The third column will show the saturated vapor. So that's why we are going to use those 3 columns if it is saturated mixture. خلاص? That is if it is saturated. But if it is superheated, the only choice you have for superheated is table F2. زين دكتورة, and you mentioned table F1 for saturated. You table F2 for saturated, but only the first 3 columns. But superheated for superheated, you have to use the remaining of the table. For the subcooled, how can I get it? I don't have any table for subcooled properties. If in the question they told me it is subcooled, then I will have a problem. And then, so the idea here is this: whenever it is subcooled, then what you have to do is the following. You have to get the properties at the given temperature. Which property? Property of liquid. ليش دكتورة? Because they found that the effect of pressure is very insignificant when they change the pressure at subcool. The effect of pressure is not that significant on the property. So what they tend to do, at the given temperature, you have to go and find out the liquid properties, because the liquid properties are the closest to properties for subcooled phase. Don't worry if this is still not clear, because what you are going to do next lecture, I would have to solve the tables. I will upload for you. I will upload supporting material. Please solve them before next lecture. Try to solve them, and I will help you next lecture to fully understand them. Last thing before I finish today's lecture, now this table just summarizes how to know the properties, if it is saturated liquid or saturated vapor or saturated subcooled. Last thing which I did not answer is the exact property here. And to answer this, let me just show you what we have in this slide. If you have a mixture property, then the way you calculate the property exactly for a mixture is using this relationship. Generally speaking, any property is equal to combination of two phases. If you have liquid and vapor phase, then you will take the property of liquid and property of vapor and you will add them together. But you cannot add them together without multiplying them by number of mole or masses. For example, if I want to find volume of mixture, Okay, you will go to the table, get the volume of liquid, get the volume of vapor, but you have to know how much of liquid and how much of vapor you have. خلاص؟ الحين based on the table, you have this in centimeter cube per gram. So in other words, you have to multiply it by gram of liquid here, and here you have to multiply it by gram of vapor. Or in terms of mole, if the unit is in per mole. إنزين. You can do that, or because the property here already multiplied by n, I can put that in terms of mole fraction or mass fraction. And as I mentioned before, I have the quality x. Because I have the quality x, then I can take the property, multiply it by x of liquid. That's for the property of liquid. For the property of vapor, take the x of vapor multiplied by x of vapor. This is how it is. So you can rearrange it by putting x of liquid as 1 minus x of vapor. And if you rearrange it, you will get this formula. Sorry, that is only if substituting. With rearranging, you will get this formula. What is this formula? Means if you want to find the property of any mixture, whether it is H or U or V or S, then bring the liquid property, bring the quality as a value, and here delta MLV means it is M of vapor minus M of liquid. And this was the evap mentioned in the table. Do you remember when I said evap that is given in the table, F1, it was the difference between liquid and vapor? M vapor minus M liquid, that we need it here. Why we need it here? Because it will show you, or it will allow us to calculate the exact quality of a mixture. So that's actually chapter 6. I finished chapter 6, but I did not solve any problem. I did not make any practice. I just explained the material related to how to read the properties from the table and how to calculate the properties if it is a mixture. Now, I want to make sure that you get the idea here. And as I said, next lecture is going to be just practical application. Anybody got any question here? Ali, what about the subcool? I said the subcool means compressed, and with the subcool, you have to go to the saturated liquid table and get the properties of liquid at the given temperature, because this is the closest value. It's an approximation, but it's the closest values to the liquid, subcool liquid properties. Okay, any question? Guys, any question? If you still have doubt, don't worry. I will upload the supporting material, 2 supporting materials. Try to define what's the phase in those tables, and on Tuesday we can discuss them in details. Any question, guys? Clear? Just write to me if it is clear, guys. I know today we did not deal with numbers a lot, so maybe you would have doubt, but on Tuesday I'm sure the picture will be so clear for you. Okay, great. I can see many are satisfied from what we explained today. So hopefully next lecture I will do more practical applications on that. Okay, so see you on Tuesday in this case.